All right, think about some of the really demanding things we do online now, like super low latency financial trading feeds.
Yeah, or those huge global software updates hitting millions of devices at once.
Exactly. Or live streaming a big sports event in HD to, well, potentially millions of people. All these things share a massive challenge, right?
Definitely.
Mm.
How do you move huge amounts of data super efficiently?
You can't just send like individual copies to every single person. That'd be insane.
Nope. And you also can't just blast it everywhere like broadcast, hoping the right people get it.
Yeah.
That would just flood the network.
It's wasteful.
Totally wasteful.
Mm.
So when you need that kind of surgical precision for data delivery, that's where multicast comes in.
Multicast.
And
Yeah.
behind multicast, there's this really sophisticated, almost invisible layer of protocols. They're specifically designed to manage group communication.
Saving bandwidth.
Incredible amounts of bandwidth. And critically, making sure only the devices that actually ask for the data receive it. Okay, let's unpack this then. We are diving deep into the core mechanisms that make this precision delivery possible. IPv4 multicast protocols.
Right.
This isn't just, pushing packets around. It's about dynamically building and managing the specialized distribution lists inside the network.
Yeah, and that's the fascinating part for me. It's not static.
Right.
These lists, or trees as we often call them, are constantly being rebuilt in real time based on who needs what right now.
So our mission today is really to understand the heavy hitters here, the main protocols making this happen. We're talking IGMP and PM.
Exactly, IGMP and PM.
Right.
We're going to explore how the network dynamically builds this, well, perfect delivery tree for specific application traffic.
And how it keeps it maintained, like trimming branches.
Precisely. How it's maintained, pruned when sections aren't needed anymore, and even extended across massive, complex infrastructures. Okay, let's start at the edge then, where the user is, or maybe their device. The moment, say, your laptop decides it wants that livestock feed, what happens first?
Well, that device uses something called the Internet Group Membership Protocol, IGMP.
IGMP. Got it.
Think of IGMP as the subscription service for multicast. It's the client-side piece.
So my laptop tells the network, hey, I want this.
Basically, yeah.
Yep.
It allows the receiver, your laptop, a server, whatever, to signal to the nearest network device.
Yeah.
Usually it's local router or maybe a switch.
Okay.
Which specific multicast group it's interested in joining.
And that group is like the channel for the stock feed or the video stream.
Exactly. Each stream or feed has a unique multicast group address. So this whole process of joining and also staying joined, maintaining that membership, it's absolutely fundamental.
Because that's how the network itself finds out who actually cares about which data stream.
Precisely. Without IGMP, the network's blind to who wants what.
Okay, so the request is made via IGMP. Now, the network needs to figure out the delivery path, the sort of geography of this whole thing. You mentioned trees.
Yeah, the tree analogy is really helpful here. So in this tree, the root node is the source. That's the device actually sending out the multicast traffic.
The server streaming the video, for instance.
Right. And then way out at the ends of the branches, those are the receivers, the devices that joined using IGMP.
And the direction matters, obviously.
Hugely. We talk about upstream and downstream. Upstream is always the direction back towards the source.
Okay.
And downstream is heading away from the source out towards all the receivers.
Gotcha. Now, you said IGMP is mainly about joining membership, but the sources mentioned a security aspect, even with IGMP.
Yeah, it's interesting. While IGMP itself isn't a routing protocol, there are security considerations even at this local edge level. An enhancement was put into IGMP version 2 specifically.
Wait, IGMP v2, if it's just about joining, where does security come in? Is this like encryption or something?
Not quite encryption. It's more about handling ambiguity,
Yeah.
which, can definitely be a security weakness.
Ambiguity. How so?
Well, this enhancement focuses on scenarios where a device, like a router, can't reliably figure out the source address of an incoming multicast packet it's seeing.
Why would that happen?
Think about maybe some specialized network TV setups or certain types of hardware that might use dynamic or even slightly obfuscated source IPs for the multicast streams.
Ah, okay. Not your standard server setup.
Right. So the IGMP v2 edition provides a way for the network device to handle this ambiguity safely. It prevents confusing or garbage traffic from messing up the group membership lists or maybe even exhausting resources on the router itself.
So it's about keeping the membership process itself clean and reliable, even with weird sources.
Exactly. It ensures the integrity of that initial group membership signaling.
Okay, that makes sense. So IGMP handles the I want this data part, but now we actually need to get the data there across potentially many routers, the delivery truck, so to speak.
Right. That's where PM comes in. Protocol Independent Multicast.
PIM, this sounds like the big one.
It is. PIM handles the really complex routing part. It figures out the actual path the data should take across the network, potentially hopping through dozens of routers.
And it connects the source, the root node, to all the members who joined via IGMP.
Correct. But PIM doesn't just blindly forward packets. Before it even considers sending a multicast packet onwards, it performs a really crucial check. It's called the Reverse Path Forwarding Check, RPF check.
RPF check, reverse path forwarding. That sounds important. Maybe like a security thing again.
It's fundamental to how multicast routing works, and yes, it has huge implications for stability and preventing problems. Think of it as the network's built-in defense mechanism against loops and inefficiency.
Loops, like the data circling around forever.
Exactly. That would be catastrophic. The RPF check basically guarantees that a multicast packet is only accepted and forwarded if it arrives on the
Wait, say that again? It checks the path back to the source.
Yeah. Does the packet arrive on the interface that represents the shortest, best path back to where it came from? If it arrives on some other interface,
Something's wrong.
right? The router knows something's fishy. Maybe it's a routing loop, or maybe it's just arrived via a suboptimal path. Either way, PIM says nope and drops the packet immediately.
Wow. So it's constantly checking that the flow is coming from the right direction based on its own routing table.
Constantly. This dynamic, ongoing loop prevention is what allows these multicast trees to be stable and reliable, even when the underlying network topology gets really complex.
Okay, that RPF check sounds vital for stability. And PIM uses this, along with the IGMP info, to build that multicast tree structure we talked about, connecting the source to all the interested receivers.
Correct.
But I'm still thinking about the dynamics. If subscribers are joining and leaving constantly, like in finance or streaming, that tree can't just be static, right? It must change shape all the time.
Absolutely not static. And this is where PIM gets really clever and efficient. Through dynamic manipulation, the two key mechanisms here are pruning and grafting.
Pruning and grafting, okay, like gardening.
Pretty much. So imagine a branch on that multicast tree. And let's say the very last subscriber device on that particular branch decides it doesn't want the data anymore. It leaves the group using IGMP.
Okay, the last person watching the stream on that network segment turns it off. We call those end devices leaf nodes, right?
Exactly. Leaf nodes. They don't have any other downstream multicast members relying on them. So when that last leaf node leaves,
What happens? Does the traffic just keep flowing uselessly down that branch?
no, that would be wasteful. The router or switch connected to that departing leaf node, or the upstream router responsible for that segment, realizes, hey, nobody downstream needs this anymore. So it sends a prune message upstream.
Upstream, back towards the source. Right.
Yeah.
This prune message is an active command. It tells the upstream routers, stop sending traffic for this group down this specific path, and this happens immediately.
Immediately. It actively cuts off the unwanted traffic flow to that branch, saving bandwidth not just on that link, but potentially on every single upstream router along that path back towards the source. It doesn't wait for some timer to expire. It's an immediate resource-saving trim of the tree.
Okay, that sounds incredibly efficient, especially for, like you said, volatile environments, financial trading floors maybe, where people jump in and out of specific data feeds constantly.
Exactly. But what about the flip side?
Right. What if someone joins a branch that was just pruned? Say a trader suddenly needs that high-frequency feed that was cut off a minute ago. Do they have to wait a long time?
Nope. That's where grafting comes in.
Right.
If a new member joins a segment using IGMP, and that segment was previously
If
pruned,
the local router knows it needs the data again.
correct. So that router immediately sends a graft message upstream.
Kind of like sticking the branch back onto the tree.
Precisely. It's an explicit request saying, hey, I need that feed again down here, please. This graft message essentially cancels out the previous prune state for that branch.
And traffic starts flowing again, instantly.
Instantly, or, well, very, very quickly, without waiting for some longer periodic refresh cycle. This dynamic cutting with prunes and immediate restoring with grafts is absolutely essential for applications where groups change membership thousands of times a minute, potentially.
So PM ensures that the high-volume traffic only goes where it's needed, stops immediately when it's not, but can reappear just as quickly when requested again.
That's the core idea of PM's efficiency.
Okay, if PM is so good at this pruning and grafting stuff, why do we have different modes of PM? the sources mentioned PM dense mode and PM sparse mode. Why two?
Good question. That initial efficiency we described, the pruning part especially, is really the defining characteristic of PM dense mode, DM. It's formalized in RFC 3973.
Dense mode. Okay. DM operates using what's called the flood and prune model, just like it sounds. Traffic for a new group is initially flooded out across the entire PM domain, or at least a significant region. Flooded first. Seriously?
Yeah. It assumes receivers are dense, meaning it assumes most parts of the network will probably want the traffic. Then, any branches or routers that don't have downstream members wanting the traffic actively send those prune messages back upstream.
So start by sending it wide, then quickly cut back where it's not needed.
Exactly. It's robust, relatively simple to get going, but it's really only suitable for networks where the receivers are actually densely populated. Maybe like a campus network where lots of users might want a common stream.
Okay, I can see how that flooding part would be, well, potentially catastrophic for bandwidth on larger networks,
Yeah.
like across a big corporate wide area network or the internet itself.
Absolutely catastrophic. You can't flood first across the entire internet. That's why we have PM sparse mode.
Can't sparse mode. Okay, so this flips the logic.
Completely flips it. Instead of implicit flooding followed by pruning, sparse mode relies on explicit joins. Traffic only flows where it has been specifically requested beforehand.
So no flooding. The default is no traffic.
Right. Traffic only gets sent down paths where a downstream router has explicitly said, yes, send it here. This works beautifully for networks where receivers are geographically spread out or sparse. Think WANs, the internet.
But how does it work then? If the source starts sending, how do the interested routers even know where the source is to ask the data if nothing is flooded?
That's the clever bit. Sparse mode requires a helper, a sort of central point of intelligence to coordinate things. This leads us to the concept of the rendezvous point, or RD.
Rendezvous point, RK,
Oh.
okay, like a meeting place.
Exactly. It's a designated router, or set of routers, that acts as a known meeting point within the PM sparse mode domain.
How does it work?
Two things happen at the RP. First, when a multicast source starts transmitting, its local router, called a designated router or DR, sends special register messages to the RP, basically announcing, hey, I have a source here for this group.
So the source registers with the RP.
Right. And second, when a receiver wants to join a group using IGMP, its local router sends a PM join message towards the RP for that group.
Ah. So receivers send their requests to the RP, and sources announce their existence to the RP.
And the RP then effectively connects the dots, telling the receiver's router where to find the source, or initially forwarding the traffic itself until a more direct path can be built.
Okay, that makes sense for sparse environments. But having just one single RP router managing all these critical streams, like maybe a global corporate announcement or something, that feels kind of risky. A single point of failure.
It absolutely is a risk, and network engineers definitely worry about that. That's why the sources highlight PIM, Anycast RP.
Anycast RP, so multiple RPs.
Yes, but it's more sophisticated than just basic backup RPs. With Anycast RP, you configure multiple physical routers to act as RPs, and crucially, they all share the exact same IP address.
The same IT address. How does that work?
Standard Anycast routing gets traffic to the closest RP topologically. But the really important part is that these Anycast RPs usually run another protocol between them, often MSCP, which we'll get to synchronize state.
Synchronized state, meaning they all know about the same active sources and joins.
Exactly. So if the primary RP the traffic was flowing through suddenly fails midstream.
Another one can take over instantly.
Instantly and seamlessly, yes. Because the other RPs are already active, they share the same IP, and they already have the necessary information about who's sending what and who wants it.
So say a live global news event is streaming using sparse mode. The physical router acting as the main RP crashes.
The network automatically reroutes register messages and join messages to the next closest RP with that same Anycast IP, and because the state is shared, the disruption is minimal, maybe even undetectable to the end users.
Wow. So Anycast RP isn't just redundancy, it's about fast convergence and load balancing too.
Precisely. It turns that potential single point of failure, the RP concept,
Yeah.
into a really resilient, high availability core mechanism for sparse mode.
Okay, connecting this to the bigger picture now, you've got these efficient PM sparse mode domains running, maybe one in Europe, one in North America, each with its resilient Anycast RP setup, but they're still kind of islands, right?
Yeah.
How does the RP in, say, the London domain know if a really critical video source has just started transmitting over in the New York domain? PMSM itself is usually confined within its own domain boundaries.
That is exactly the problem that MSDP solves, the Multicast Source Discovery Protocol.
MSDP source discovery.
Okay, think of MSDP as the glue between different PM sparse mode domains. Its whole job is to allow the RPs in these separate domains to share information about active sources that have registered locally within their own domain.
So it lets RPs tell other RPs about sources they know about.
Essentially, yes.
Hmm.
The key piece of information they exchange is called a source active message, or SA message.
SA message. Okay.
Okay, so if a source starts transmitting in domain B, New York, its local RP receives the register message. Then that RP packages up the essential info, the source address, the group address, into an SA message.
And sends it where?
It sends it to its configured MSDP peers, which are typically the RPs in other domains, like the one in London.
So the London RP gets this SA message and learns, aha, there's an active source for group X over in domain B, and that RP knows how to reach it. That's the core operational flow. It's like sending out a bulletin. Source active for this group, originating in my domain. If your receivers want it, come ask me. And this allows receivers in London to ultimately join the stream originating in New York, even though they're in different PMSM domains.
Exactly. MSDP bridges that discovery gap. And just like with RPs needing redundancy, you need reliability for MSDP peering too, especially in huge global networks. That's where MSDP mesh groups come in.
Mesh groups, more complexity.
Well, it's about resilience again. RPs within the same region or domain can be configured into a mesh group. This means they coordinate among themselves to reliably exchange those SA messages with peers in other external domains. It helps ensure that source information gets propagated reliably, even if some intermediate routers or links fail.
Okay, so MSDP handles discovering sources across domain boundaries. But with all this dynamic traffic potentially flowing everywhere, triggered by joins and graphs and SA messages, you must need some controls, right? Some safety valves.
Absolutely. You need to protect the core infrastructure.
Yeah.
And one really crucial point the sources detailed was the need for a PIME register message rate limit.
A rate limit on those register messages, the ones the source's first router sends to the RP. Why is that specific message so important to limit?
It's all about protecting the control plane of the RP router itself. Remember, when a brand new source starts transmitting, the very first packets it sends get grabbed by its local DR.
The designated router, yeah.
And that DR wraps them inside these PM register messages and sends them directly to the RP's control processor.
So it's not just data plane traffic yet, it's hitting the router's brain, basically.
Exactly. Now imagine a source suddenly bursts out hundreds or thousands of packets in the first second. If the DR dutifully encapsulated every single one into a register message,
It could just overwhelm the RP's CPU, like a denial of service attack from its own source.
precisely, it could completely swamp the RP's routing engine, preventing it from doing its main job of processing joins, prunes, and actually routing. So this rate limit acts as a vital safety valve.
What's a typical limit?
The default is often quite low, maybe just one register message per second globally, because you're protecting that central control plane. You absolutely do not want one misbehaving or just very bursty source to accidentally bring down the RP for everyone.
But you can adjust it if you have a legitimate high-rate source.
Yes, engineers can tune it. The sources mentioned may be allowing up to, say, 50 packets per second to be registered for certain trusted, high-throughput source group pairs. It's a balance between safety and accommodating application needs.
Okay, that protects the control plane. But what about controlling the actual data flow? The data plane. How do network operators make sure only, say, authorized subscribers get the confidential company-wide video stream? Or stop unauthorized sources from injecting bogus traffic into a multicast group?
That's where multicast boundaries come into play. Network engineers use commands, often like multicast boundary, configured directly on router interfaces.
A boundary on an interface. What does it do?
It acts like a filter or a gate. It lets you strictly control which multicast group traffic is allowed to pass through that interface, either coming in or going out.
And how do you define the rules for that gate?
Typically using standard access control lists, ACLs. You write ACLs that specify which multicast group addresses, or maybe even which source and group pairs are permitted or denied.
So you could say only allow group 239.1.1.1 through this interface, or maybe block anything coming from this suspicious source IP.
Exactly. And it gets even more granular. You can use ACLs to define explicit PIM join and prune policies. So you can configure an interface to only allow PIM join messages for specific authorized groups.
Ah, so even if someone downstream tries to join an unauthorized group via IGMP, the PM join message gets blocked right at the boundary router.
Precisely. It's policy enforcement right at the network edge or at key internal choke points. It creates a sort of mandatory walled garden, ensuring only the intended traffic flows and only authorized members can join.
Okay, that seems critical for security and controlling resource usage.
Absolutely essential in any production multicast deployment.
Wow, okay. So we started this dive just thinking about efficient group delivery, but we ended up deep in the mechanics of how the network dynamically builds, maintains, and prunes this perfect delivery tree using PM.
Right, with all the pruning and grafting.
How the clients at the edge signal their intent using IGMP, and then how these separate PM domains can discover sources in each other's territory using MSDP, all while keeping things stable with RPF checks and safe with rate limits and boundaries.
Yeah, it's quite an intricate dance. And it really raises the question, what's the actual day-to-day operational impact of getting all these knobs and timers right?
What do you mean?
Well, the ability of these protocols to manage membership and traffic flow so dynamically, especially those near-instant responses with grafting and pruning, coupled with protective measures like the register rate limiting or those strict boundaries, it's absolutely fundamental to the stability and scalability of the services we rely on.
Like the video streaming, the finance feeds?
Exactly. So now, when you hear about network engineers obsessing over, the PM prune timer settings or the IGMP group membership interval or designing their RP strategy, you have the context. You understand why those parameters are so critical. They directly impact performance, stability, and resource usage for these demanding applications.
That makes sense. It's not just theoretical. Okay, so for a final thought, the source materials we looked at, they also touched on something called PM convergence on MCARA address movement.
Ah, right. Layer 2 changes.
Yeah. We've been talking mostly layer 3 routing complexity, IP addresses, routers. But underneath all that, the actual physical devices, the source server, maybe might change its physical connection point. Its MASI address might appear on a different switch port, layer 2 stuff.
Which can definitely happen, especially in virtualized environments or with device mobility.
So PIM, this complex layer 3 routing protocol, needs to be smart enough to handle that underlying physical shift, that layer 2 change, without completely breaking the established multicast routing paths above it.
It needs robust mechanisms to reconverge quickly when the source effectively moves at layer 2. So here's the thought to mull over. How does this requirement, maintaining a perfectly smooth, uninterrupted multicast flow for potentially thousands of users, despite the physical devices underneath maybe shifting their location, how does that capability fundamentally change how we should think about overall network resilience, and maybe even the seamlessness we expect from our internet experience today? That connection between the logical multicast routing and the physical layer underneath and keeping it seamless, yeah, that's definitely something interesting to chew on.